Okay, I'm quickly going to summarize what we are going to be doing in shading parts, uh, so that you understand the whole algorithm, whole ray tracing algorithm, and then we are going to start going over the slides and start talking about the details of those parts. Okay, so here is the picture we have right now. We have a ray. Uh, let's have a surface. I'm going to zoom in on our sphere, for example, and we have an eye point E. And imagine, let's focus on now a single ray that is looking, and this is our ray equation. Let's call this R. And our ray hits a point, and this is a sphere, for example. Our ray hits a sphere, and now we have this point, and our goal is to correctly compute the color of this point on the sphere. Now, there are a couple of things. First of all, we're going to be executing an illumination model. This is called the basic illumination model, which is going to come up in OpenGL part as well. This basic illumination model is composed of three very simple components: ambient, diffuse, and specular. Okay, sometimes the specular part is called Blinn phone shading. This is diffuse part is sometimes called Lambertian component, so Blinn phone. So these are the researchers who contributed to these parts of the model. This is, I think, if I'm not mistaken, it's called Lambertian. We are going to go over the slides, and this is the ambient component. So, and the parts that they model is, as I said, ambient is the simplest case. Ambient is independent of the light source. Therefore, usually we are going to run the model like this. For if our ray intersect with an object here, the first thing we are going to do is, regardless of any light sources in the scene, we are going to add the ambient component. And the ambient component is going to be added like this. The ambient color in the scene is going to be identified as a light source, for example, with intensity 50, 50, 50, or maybe even something smaller, all over the scene. Okay? The intensities of the other light sources, or maybe let's not talk about the attenuation, the light intensity decrease with respect to distance yet, when we come to the other light sources, but let's assume this is something small, maybe 20, 20, 20. So the way the color is computed is that we have a light source with some intensity. We are going to conduct an operation with two vectors, which is neither a dot product nor cross product. I don't know whether this operation has a name. Which actually is going to compute this sphere, for example. It's a red sphere. The way we coded the red sphere was saying that it reflects, for example, 100% of the red color, and maybe if it's like this pastel pinkish red, we put it reflects 30% of the green color, and it reflects 30% of the blue color. So the way we indicated the color of this sphere was by writing what we call the reflectance coefficients. So these are sometimes called reflectance coefficients, which means that it's the color of the material, the reflectance coefficients. It's reflecting this components of the white light. Okay, 100% red is reflected. So the first thing when we're computing the color on the surface is to we multiply basically the way we compute color with the reflectance coefficient and the intensity of a light source is, as I said, to do something interesting with these two vectors. We multiply these two vectors and get another vector, but it's like a combination of, or it's partly dot, partly cross product. But it's something very simple. We just say multiply 20 with 1.0, it's 20. Multiply 20 with 0.3, it's 6. multiply 20 with 0.3, it's 6. So we get this 26,6 vector. Look at this 26,6 vector. It's a vector, RGB. It looks 20 units of, and then at the end, for example, we're going to make sure that the values here are always between 0 and 255. I'm going to be maybe converting this will be my pixel color, but the ambient component is just computed by multiplying these scalar values at each color channel separately. Okay, and the color model that we're applying is an additive model. So whatever contribution we get to this point from any component of the model or from any other light source is going to be additively applied to the color we compute here. When I compute the diffuse color separately, I'm going to add the diffuse component one by one to my color, to the red channel, to the green channel, to the blue channel. So the color is really accumulative. The components either contribute 0, there is no negative color, there are no black holes in our ray tracing. We're not going to go into black holes, and that's physics stuff in our computer graphics course. So every material either emits 0 amount of light or they emit some amount of light. They do not absorb, get light rays and absorb them. Okay, so there are no negative light intensity values here. It's always positive, and it's additive. That's another thing. One thing during these additions is that since it's all additive, if you have many light sources in your scene, what happens when these values go beyond 255? This is what we call, which happens in real life in cameras too, in physics, this is what we call saturation. Saturation, it means that that green value has achieved its brightest, largest value, 255, and all the values, even if you add more light sources to this red component or green component or blue component, this is the maximum it can get. This is the brightest white or brightest red you will be able to get. This is sometimes called clamping. We are going to cut any values above this value to 255. Okay, so this is something you practically face when you're doing your ray tracing. Some values may be greater than 255. Make sure that you clamp them back to 255, which is your largest value. The red levels we have in our scene, the intensity values, range from 0 to 255. But yeah, in ambient component is very simple. This ambient value, the ambient light source, that's just apparent everywhere in the scene, is going to be given to you as input in the scene file. This is something, that 2020 value will be given to you as some parameter. That's the ambient light source. And your sphere's colors, they will be given to you as well. So for any point on the sphere, for example, this 26.6 is the default value of any surface point on the sphere. So that's the darkest default of this sphere you're going to see on your screens. It's basically saying that. There is no, these are all the ambient values. It all depends on the user. I mean, if you want your scene to be lighter, you may increase the ambient value. If you think that your scene appears too dark, you can light up your entire scene by increasing the ambient value. But you'll see that when you increase the amp value, this is really aesthetics. I mean, there is no up limit. But when you, for example, make the ambient, for example, 200, 200, 200, you may see that your entire scene is very whitish. Everything gets saturated. At some point, your image is just going to burn out. It's just going to be whole white. Okay, so that's maybe the up limit. I mean, you don't want your scene to be too bright. The details of your scene are just going to disappear after many of your parts of your scene are going to saturate. So it's like leaving the film outside in the sun. So you won't get anything at the end. So there's no, but those are very good questions. So many of these things here you're going to see Some of them are really aesthetics, and you just try different values. There is no upper limit. This is just a model. Oh, exact. That's a very good point. The ambient could also be, instead of having light intensities between 0 and some arbitrary values, we can also have them between 0 and 1, so that we apply directly to integer RGB values at the end, which are between 0 to 55. So whether these sphere color values are between 0 and 1, or your intensity values are 0 and 1, that's really implementation dependent thing you need to decide on. So you need to read that part of the specification of the assignment carefully, how this ambient is given to you. There are no rules for that. Different people have different implementations of how they represent these intensity values, whether to represent intensity between some 0 and 1 or some 0 and very large number. It really depends. But the main thing is that whatever your ambient value is, to take into account different colors of materials in your scene, you multiply your ambient value with the material reflectance coefficient. With this type of multiplication, multiply RGB values separately one by one to get another vector 3, which is your RGB colors. But it really depends. Now, ambient is the easiest part. It's given to you as input. That's the default color that is apparent on all surfaces. But only if your ray intersects that point, okay? Because we are interested in the color of this ray. That's what our pixel value is. For example, if there is no ray that is intersecting a point on the sphere that is behind, that part is never going to be seen. That's never going to get to a pixel on the image. So those parts are really irrelevant. It's like a philosophical question. It's like, is it really there if we don't see it, for example? In our case, since it will not even be there, it will just be existence. Its existence will be like a mathematical equation, nothing more. So it will exist as we see it. As I said, this is like a philosophical existential question for the spheres, but yeah, anyway. So but the diffuse and specular component, it's computed per light source, which means that actually this part of the equation is like in some kind of a for loop in an equation for each light source, from the first light source to the nth light source in your scene. If you have many light sources in your scene, you compute the light source diffuse component due to light source I, you compute the specular component due to light source I, and you add them up, and you add everything to that ambient component. So if you have multiple light sources in the scene, again, the contribution of different light sources on this point are also additive. Okay? Now, I crowded many parts of this slide that actually now I'm going to erase some parts. So because I need to use this figure, this surface, to show you how diffuse is computed, how specular is computed. So I'm erasing these things I have written. But meanwhile, if you have any questions, feel free to ask them. Yes. Yeah, I think instead of doing the efficiency thing, I think you should have some working ray tracing coded, because making certain parts efficient later is not difficult. For example, making the intersection test more efficient by implementing a data structure in it. But this is not a must part of the assignment. If you just implement the most basic parts, you're going to probably get a full grade 100. If that's sufficient for you, you don't need to worry about making your ray tracing faster. But yeah, you should first code. I recommend coding the entire ray tracing algorithm first, even if it's slower. Okay, to see the entire nice picture, generate the picture. If it takes 1 minute, that's okay. But you'll see that making it more efficient, building it data structure to do the intersection test make it super fast, but you're not required to do that. These small optimizations, like pre-computing certain things that can be taken out of for loops, taken out of generation of rays, like pre-computing the normal vectors of the triangles. They are optimizations that you can do afterwards, after you have your ray tracing code. So first, implement each one. And I recommend you, just like we did in class, implement your ray tracing step by step. Checking your bugs at every step. For example, did you generate the rates correctly? Did you compute the diffuse component correctly? Step by step, the image you generate is going to gradually, incrementally get higher quality at every step. In shading, for example, implementing the basic illumination model is not very difficult, but you can first try to have ambient and diffuse only, and see how your spheres look like. Then add the specular component. It's everything, the quality of your image is going to get, as I said, gradually better. Every step of the ray tracing algorithm is something, a module you add to your existing ray tracing code. So you can continue doing like that. Diffuse component tries to model light rays that, assuming this point on the sphere actually diffuses the incoming light rays. For example, if there is a light source here, the light rays that reach this point, it is diffused, it's reflected in every possible direction. So this is what this diffuse component tries to model. But it also tries to model this. The fact that if, for example, you have a surface that is like this, and you have a surface that is like this, and if this is your light source, okay, if this is our light source, if I have a light source here, in physics, it's a known fact that the amount of light reflected off the surface of this one, in which the normal vector is facing directly. So the amount of photons that are going to be released from this surface, that are going to be reflected from this surface, is going to be more in a surface that is like this compared to a surface that is like this, in which the light rays again hit this. So the light rays are hitting this point like this. By the way, you can say that, what about light rays coming here? I mean, if you consider the light rays here, again, it's, I mean, basically you cannot make generalizations about the entire surface. Whatever we're talking about a single point on the surface. Okay, so different points on the surfaces will have different light vectors. Their normals will be the same, but light vectors will be different. So just focus. I'm focusing currently on a single point. For example, on this point on the surface, and I'm looking at these two vectors, the light vector and the normal vector. And here, this is the normal of the surface. So basically what it says is that if the angle, as the angle between the light vector and normal vector gets large, the amount of photons released or reflected off the surface is reduced. There's the rule about this, I think, is like the flux rule, or there's a physics. I mean, if you take optics class or just simple high school physics, I think there's a this has a name. Okay, the scientists who found about these things contributed to how linearly, for example. Yeah, exactly. This is what we're going to do. We're going to check, for example, if I have these two light, the normal vector and two light vector, let's call this two light vector, to indicate that they are both facing in the same direction from the surface point. If you look at this angle, if the cosine of the angle is 0, cosine of the angle is 1, which means that angle is 0. If alpha is 0, the cosine of the angle will be highest. we have the highest amount of light that is reflected. And the lowest amount of light that is reflected happens when our surface, or when our light ray just grazes the surface. If this is my surface, it will be my normal, and this is the light vector. The angle is alpha is equal to 90 degrees. No photons can be reflected. At this point, when alpha is 90, cosine alpha is 0, and that's when no amount of light is directed. And also, if the cosine alpha may be negative, it means that the surface is looking at a different direction. For example, you may have a light here. Look at this. This is the light vector from this point. And this is the normal vector of the surface. Look, this is the normal, and this is the light vector. Light is behind the surface. So this is where that front of the triangle, back of the triangle comes into picture. Depending on, for example, if this is a surface, if the surface is looking this way, it means that this is the back of the triangle that is looking at this, and whether you are going to illuminate the back or not depends on different things. But if you're going to illuminate the light back, even in that case, you should have a normal vector for the back surface that is like this. This one again is less than 90 degrees. So if you're interested in the front surface, its normal is facing this way. When the angle between that and the light vector is larger than 90 degrees, I mean, as you can see, the light rays cannot reach the front of this surface. It's facing backwards. So that's basically the diffuse model. The only thing that we do is, in the diffuse model, is we form this to light ray. Okay, if you normalize this to light ray, and if this is the normal of the surface, we have two vectors, normal and light. Imagine they're normalized vectors, which means that their length is 1. When their length is 1, the cosine of the angle between them will be given directly by their dot product. So you find that their dot product for the cosine of the angle, and you multiply this. So basically, the diffuse component is that whatever your diffuse lighting intensity, whatever the intensity of light is, for example, the intensity of the light source, you multiply that with the cosine of that angle. In other words, you multiply your I alpha with the dot product of your L, and you, whatever this intensity is, you find the intensity just like this ambient 2020, and then you multiply this value with your reflectance coefficient, which was 10303. So this gives you the intensity of the light that hits this point, the amount of photons that are going to be hitting this point in diffuse component. And it's actually they're reflected off this point. But also, when we take into account the material properties of the sphere, for example, out of this many photons, all 100% of the red photons and 30% of green, 30% of blue photons are reflected. So you multiply it again with this K. But the multiplication that I have here with this reflectance coefficient vector, let's call this K, this vector we have here, by the way, this is a vector, as you can see. This n dot product L, cosine alpha, is a scalar value. But this I3, the intensity of the light, again, is given as RGB values, RGB channels. So it's a three-dimensional vector. You multiply it with this other three-dimensional vector with this not dot product, not cross product kind of multiplication. Let's call it color multiplication. We use color multiplication between the reflectance coefficient and this to compute the diffuse component for this light source. So the diffuse component from this light source, di, is equal to this. Okay? And the last component, which is the specular component, let me get a different. So for every light source, we're going to be adding these things. And we need to check if this n, we can put a function in front of this nl, like a clamp function. Whatever the dot product is, whatever its value is, we are going to be clamping it between 0 and 1. So if it's a negative value, negative values are going to be clamped to 0. They will have no effect. Okay, you can write a clamp function. Actually, this clamp function actually exists in GLSL. It takes two parameters, minimum, maximum, clamping values. Whatever the third parameter you give to this, if its value is less than the minimum one, it's treated as the minimum one. Its value is larger than the maximum one, it's reduced to this maximum one. So you need to have such kind of a function. If it's less than 0, just treat it as 0, this dot product. Yeah, and the last 5 minutes I'm going to talk about the specular component, and it's just going to be added like this. And the specular component, again, let's consider R light, R ray, and this point. So this is the normal vector, and imagine we have a light source that is here. Okay, so this is the light vector. Now, specular component actually is used to model mirror reflections. The Lambertian model, the diffuse model, assumed this incoming light ray was reflected in every direction, right? Now, the specular model tries to model the light ray that is actually reflected in a specific direction. If this, for example, if this surface was a very perfect mirror, what will happen is that the angle of incidence is going to be equal to the angle of reflection. Okay, so and if it was a pure mirror, we would be able to see the photons coming off this light source only if our eye was alongside this reflected ray. Because if it was a pure mirror, there will be no photons reflected in our eye's direction. Okay, we will not be seeing anything. That spot is going to not reflect any light rays towards our eye. Okay, so let's call this, this is alpha, and let's call this ray the reflected ray, which can be computed. Okay, look at this L, look at this, given this normal of the surface, if you know the normal vector of the surface, by using the normal vector and the light direction, you can actually compute this R vector, okay, by making by knowing that the incidence and reflection angle will be the same. So you can figure out this geometric problem later. In this last couple of minutes, I'm not going to talk about that. Maybe on Thursday I'm going to talk about this, but we will not be actually computing this reflected ray. We will be using a different heuristic to compute the specular component, but it's basically this, the specular component. It checks the angle this time between your viewing ray, let's call this ray V. Actually, this is our ray R, right? I mean, basically this ray V is minus R. This was my ray's direction. This was my ray's direction, because ray was something like a line. It had a starting point, but if you think about the direction of the ray, if you just take the negative of that direction of the ray to indicate the vector towards the eye, okay, now if the angle between, let's call this angle between R and V beta, the smaller the angle beta this time, for example, the shinier we are going to see this point. You see what we're trying to do? It's like, since it's like a mirror reflection, imagine a mirror that your friend faces towards your eye. I mean, you will, if the reflected ray is closer to your eye, you're going to see that spot as a shiny spot. So the specular component takes into account this and says that if this V and R is small, then I need to have a large specular component. And the way it is done is, again, like the cosine beta. So let's compute cosine beta. But if we just multiply the intensity of light source with cosine beta, in which beta is cosine beta, this time it's going to be V dot product R, right? If these are normal vectors again, cosine beta is going to be given by V dot product R after we compute R from N and L. As I said, we are going to use a different heuristic named the half vector approach, which is going to give very close results to this one. But basically, it's the specular component is this. But if we use it directly like this, it doesn't model very shiny surfaces, because what will happen is that even if my eye is far away, I mean, look at the angle. If the angle between my V and R is between 0 and 90 degrees, even if my eye is very far away from this reflected vector, it will still have a specular component. We don't want this. I mean, we basically, it's like it will span a 90 degree. If you just have cosine beta, the values will range from 0 to 1 when the angle ranges from 0 to 90 degrees. So it will be like a diffuse value between 0 and 90 degrees. So we want actually the specular value to decrease really fast. That's another idea. 1 plus cos b could be done. That's another idea. But what they did was they want this cosine alpha value actually to decrease to 0 quickly as this beta value gets larger. So for values of beta is equal to 0, we want a large coefficient here, but we want this function to drop quickly as beta is increasing from 0 to 90. How can you make something drop quickly to 0 as this beta increases? Remember that this cosine beta is going to be a value between 0 and 1. Okay, if something is between 0 and 1, and if you want that value to decrease to 0 as quickly as possible, basically you exponent it. You take, for example, a certain power of that. Exactly, that's the solution. Take an exponent, and this is actually this is a parameter of the material that we will have in our scene file. In our scene files, if we want objects to appear shinier, we want this exponent to be a larger number. For example, 5 to 10 is a typical number, but if you give an specular exponent, this is called specular exponent, it will be some material property. If the specular exponent n is like 50, it will appear shinier. That's shinier actually for point light sources. The effect is going to be like counterintuitive, which means that that shiny spot is going to get smaller, but this is how mirror-like objects behave, right? I mean, if you have a point light source, the shiny region should be really like point light, because it will be smaller. As the angle between your view vector and the reflection vector gets larger, that should diminish quickly. So this is exactly what the specular model is. Basically, the original specular model is exactly this one. I times the cosine of the angle between them. So, or let me write it like this. I times the dot product of V and R vectors raised to some power n. I think S is used to indicate specular exponent as an acronym for specular exponent. I think S is used on the slides. But this is the specular model. For each light source, we compute this, and that's the whole shading model that we are going to have for this thing. But this computing the R vector requires actually some operations between this N and L vector. An alternative approach, which is the half vector approach, is this. What they do is, so I'm going to finish the lecture with this half vector idea. What if, look at this view vector. This view vector is already given. It's very simple, right? Minus RD is the view vector. To light vector, we already computed in the diffuse component. Now, if I take the half vector between V and L, like V plus L divided by 2. Okay, let's call it half vector H. Okay, and look at the angle between H and N. What I know is that, for example, if H was directly on top of N, what does it mean? It means that V and R should coincide, right? I mean, if this V and R were exactly the same vectors, were in the exact same direction, they will be the normal vectors. Since the incidence angle is equal to the reflection vector, the n vector should be exactly in the middle. So if that's the case, why don't we just inverse it, saying that let's compute the half vector between v and l first, and check how this half vector is close, how close it is to the normal vector. So this kind of approach avoids the computation of reflect r vector directly. We simply compute the half vector and we look at the dot product of the half vector with the normal of the surface, and we replace this part vr with that half vector idea. This, you will see that you may find counterexamples, or you may see that numerically these two are not exactly equal to each other, okay? But this still gives a very good approximation to this, and that's why in practice people use this half vector idea. So it's written here, let's see where it's in Bilin-Fon shading. The half vector is computed here. Yeah, the half vector. Let's look at where it's computed. Yeah, the half vector basically is we just add these two vectors. Actually, we don't divide it by two. We want this half vector to be normalized, so we just divide it by the length. So we just normalize it. Add these two vectors, light vector and view vector. Add them, then normalize the vector. That's your half vector. And the angle between the half vector and normal vector is the thing that you use in the specular component. As you can see, the specular component is raised to some, where is that? Yeah, the CENG exponent. It's called the CENG exponent or specular exponent. We raise it to some power to have this model. And this one shows nicely, this is the diffuse whole, our spheres look like this right now, as you can see. This is how our spheres look like now. With the specular edit, it will look, I mean, this doesn't look very realistic, but still this is a more shinier object. But the specular exponent will add this specular spot, the shiny spot, to our objects, which will help us model shiny surfaces. But there's still no reflection from other objects. Okay, so this is different. This is just the specular component from the light source, and they're all added. We haven't, the only remaining thing in our shading model, the two things are shadows and reflections from other objects. After we discuss these two things, it will finish our discussion on ray tracing. Okay, so but right now we have you can try and implement, I mean, you can have our spheres to appear like this. So the basic illumination model is done. And you should be able to, so this is diffuse plus ambient plus specular. So this is that specular spot. Putting it all together, we just add them. Okay, and then as I said, the remaining things are shadows and reflections, and we will finish those on Thursday. But go ahead and, I mean, if you can finish up to this point quickly, and as you see, the ray tracing algorithm is not so complicated up to this point. You will be able to see certain nice pictures right away. Okay, they will not have any shadows or reflections, but still they will look nice. And by the way, in OpenGL there are no shadows and reflections, so you will have OpenGL quality images by default if you just implement these parts. All right, let me stop recording now.